Welcome to another video about the basics of programming. Today I want to start a little tutorial series on the topics of generics. You may have heard that there's a new Golang release from March 2022 that brought generics, which are a feature that is known from several other programming languages, and it has been requested for many years, basically since the release of Go 1.0. In this first part of the tutorial series, we are going to look at how programming looks like when you don't have the option of using generics. Therefore, we will implement a very simple data structure, a set, for a specific element type, namely strings. So let's jump right into it. What are set data structures? Maybe you know of them from other programming languages. They are a data structure that holds unique elements. So you can put an arbitrary number of elements into a set, and the set holds exactly one element of this particular value. So if I put, for example, a number into the set like a 7 and a 3 and maybe a 9, and then I add a 7 again, there is no second 7, there's only one 7 in it, so all elements are unique. And this can be useful sometimes during programming. For example, imagine you want to read words from a file and you want every word to occur only once. Or maybe you have a list of names or addresses or something else, maybe telephone numbers, and you want to make sure that duplicates are eliminated. So that is one important characteristic about sets. They are very similar to hash maps in a way that they provide fast lookup because the element values are hashed. Maybe you've seen my earlier tutorial on maps and slices. If not, feel free to go ahead and have a look at it, or maybe later. And the basic difference is that with sets you don't really care about the associated value because you're just interested in the keys, and all elements in the set are keys that are actually hashed in the case of a hash set. So let's jump right into it and start our implementation. As usual, we need a main Go file, or at least a file where we start with package main and a function that is called main, which is the entry point, just to check that it actually runs. We're going to print hello world. Save and run it, for example, with go run main.go in your source folder. So that works fine, and we also want a test file because data structures can become quite complex and they are very important, so we want to make sure that they work as expected. So that is our first test, and just to see that it runs, we run go test, for example, with the verbose flag, and it passes because there's no code in it and we didn't let it fail in any way. Okay, so what is a simple way to build a set in Go? Well, you may have noticed that Go actually has no standard type for sets, and that is because you can simply use a map for that purpose. And that is exactly what we're going to do, but we will build a type around it and basically wrap a map type and add some methods on it so it's more comfortable to use. So if you just need a set once in a while, then it's perfectly fine to use a map. If you use it quite often, or maybe you find yourself creating little helper libraries, or maybe searching for an implementation in the internet, then it is definitely an option to use a dedicated type for that. And we are going to build it for learning purposes about generic types later. So applying what we've learned in earlier videos, we can define a new type like this using a struct. And we're going to use a map internally, so I'm going to call it internal map. We want to create the set for string types, so key will be string, and the value doesn't really matter because we're just interested in the keys. But we have to give it a value since it's a map, so we're just going to use the most simple and smallest type, which is bool. So every value that you put in here will get value true assigned. We will make sure that this happens. So something that is very common is to offer a new function for this type. We will find this in standard libraries and third-party libraries. It is basically a simple way for the user to construct a new set, and especially with more complex structs and other types, it can be more comfortable to use these instead of initializers. So we allow the user to pass an arbitrary number of elements. So we use the var_args notation, 3 times dot, of type string, which is basically just a slice under the hood, but more comfortably to use because you can just list all the elements one after another. And then we need to add the elements to our internal map. And let's actually add a first method before implementing the new function, which is size, and it's just going to return the number of elements in the internal map. So we're going to write a method, so we need this method receiver here, value receiver in our case, since we just want to read. And we can return the length of this internal map, so by using as I address this struct. And if you're a little confused about it, feel free to read up about it or look at my tutorial about methods from earlier times. Since we have this size method now, we can write a first test case, which is a good thing. So I'm going to call this test set strings because we're going to put strings in there. I create a new test with the new function, and let's pass some strings which are maybe color names, so red, green, yellow. To demonstrate that we store unique elements, we just try to add red another time. And of course we need to return a set here. So let's do the minimal implementation, which doesn't work yet, which is this: just create a new set and return it. And now we want to assert the size of the set. So set.size should be 3, right? Because red is duplicated and we want to store unique elements. If it's not the case, we want to terminate the whole test case, so we use fatal F. And let's immediately create a little helper here to avoid code repetition. I'm just going to call this check int, and we pass the testing helper and expected and actual int. So we can move it here and make it reusable. So if expected is not equal to actual, we want to fail the test. And as you've probably seen in one of my earlier videos, we can use the t.helper flag to make debugging our tests a little bit easier. Then it will show us the actual line from the calling code where the test failed instead of the helper code line, which is often not that useful for finding bugs or places where the test failed. So let's see that the size is actually 3. Pass the parameters, call set.size, save and run our test. And it fails because we didn't implement it yet, so it's very test driven. Of course, we write the test in this case first. So now we got a set with an empty internal map. Let's add the elements to the map. So we're first going to try if this works, iterate over the elements, and yeah, we have to create the map first. So I'm going to call this internal map 2, and we could use make, but I personally also like the other notation like this, so it's an empty map at first. And then internal map key is element, our string. And as I said, we just, of course, we need to use the range keyword. We just assign true because we don't really care about the value. We care about the key in the map. So the compiler complains, and that's because the first argument, of course, that is returned, first return value of range is the index, which is an int. So we actually want to ignore this using the underscore operator. And the second is our element. Now what's missing here? Our test case would show that, but you can already see it. We need to pass the internal map to the set to actually fill it. Simple enough, right? Let's test it. Okay, so this works. So far, so good. Next, let's just add the add function. So we're going to call this on a set pointer this time, which is a good idea because we want to modify the set. We pass an element, and that is a string. We're going to return nothing because we don't really need to return something. And we add it to the internal map, so s.internal map element, again, we'll just assign true. So let's see if this matches with our size behavior. I'm going to add another string, let's say blue, which should increase the size to 4, right? Because there's one more element inside it. And then when we add maybe green again, it shouldn't change the size because green is already contained and sets contain unique elements only. Let's see if this works. Works fine. So as you can see, using a map, it's pretty simple to implement. Next, let us implement remove. And I'm going to start with the test first. We are trying to remove a specific element from the set. So let's call remove for maybe red. And the size should decrease to 3. When we do that again, it should not change anything because we already removed red. So there's nothing more to remove. We store only unique elements. Size should stay at 3. How can we do that? Well, one option would be to just set the element false, and then we could do some distinctions, but we would need to adapt size. Then we need to count the number of true values in the map, because length will just give the number of all elements independently from their value. But much simpler is to just remove the complete key value pair from the map, and you can do that with the built-in delete statement. As the documentation says, it deletes the element with the specified key. So we can just say delete element from internal map. It's actually, let's see, like this, right? And it passes. Wonderful. So next we want to add a contains method. Because usually what you want to do is you want to check if an element is contained in the set or not when you write some logic based on that. And moreover, we want to make our tests better and actually check that the right elements are contained. Right now we are only verifying the count of elements. So there could be, strictly speaking, there could be something unexpected inside the set. So how would contains look like? Well, we would call it like this and pass the element and get a boolean so that we can actually write something like check bool, and I would expect it returns true for red, also for green and for yellow. But not for blue yet because it has not been added here. It is added here though, so that's where it should switch to true. And green is already contained, so nothing new there. Here red gets removed, so contains should switch to false. How does our test helper look like? Pretty similar to check int, so that's something that we can make more generic later. But for now, let's just write this for our specific type. And you can already see there's not much of a difference here between the code. It's just the types in the parameters. So that's another thing we can improve later. So let's actually build contains. Our value receiver is enough. We don't need a pointer receiver here for this method. We just want to read the value that can be copied. It's not expensive for a string. And let's see. Actually, we want to return a boolean, not a string. So true if it is contained, otherwise false. And we can just do that by checking our internal map. So internal map key element returns a boolean, and we know this is true for every key that actually exists in the map. If it does not exist in the map, Golang says that we return the default value, and the default value of booleans is false. So since we only store true values for keys that are existing, we can just return the value. Missing key will result in default value, which is false for bool types. Alternatively, what we could do instead, if we didn't have this comfortable default value, we could say look up the value, ignore the value, and instead use the second return value, which is a boolean, which you can use to actually check if the key was contained, and then we could do this. So you will see, let's actually verify this. It should work, and it does. But as I said, we can simplify that due to the bool behavior and due to the fact that we are setting true values only. And it works as expected. All right. So far we implemented quite a few simple methods. What we want to do in addition is to add a slice method. So maybe I have a program which does some things with a few sets, and then I want to have a slice with the elements, and I can simply add another method for that. So how would that look like when we specify it from a test? So a user perspective maybe. Well, I could say something like slice is set.slice, then we get a slice out of the set. So we lose these characteristics like fast lookup and unique elements, but we get the elements that are inside the set in a slice. So they will have an arbitrary order, but only one element per value. So I would expect to receive something like, in this case, red, green, yellow, but the order is not really defined. So we have to write a check like check contains, and then pass the slice and check that it contains red and also green and yellow. Then here I would expect that it also contains blue. Actually, we can inline this here since we're only checking it for one element, and here I'm using a variable to not repeatedly call it without the need. And of course here it should be green. Like this. Okay. So important, this is not the contains method that we are testing, but we are checking that the slice is actually containing the element. Or maybe we can do that even better. We could write check equals in any order. That would be another option to do that. But for now, let's just write it like this. So let's write the toSlice method. And again, it's a value receiver. We need to copy toSlice anyway. We don't need any parameter, but we want to return a slice of strings. And first, for a minimal example, let's just be naive and return an empty slice that should fail the test. So yeah, it also says check contains is undefined. And that is because we didn't yet there's toSlice. Let's limit slice like here. We need to specify this check contains helper. So check contains will look a little bit different. It will expect a slice of strings. And we will get a string that we expect, so expected. And what we can do to simplify that, actually let's do it right now to make it shorter, is we can just say we allow multiple expecteds and expected strings, or let's name it elements. And then we can simplify this code and write something like this. So we can actually make this a bit shorter here. And include the old elements too. So just going to check for the other elements in addition. And then, is green in here? Yes, it is. So that doesn't change anything here. But when red is removed, we want to check that is no longer the case. So we remove that. All right. Now let's mark this as a helper function for simpler line printing. And we just run over the expected elements. So again, you can use a range loop. And no, yes, that's the index. So compiler's complaining because I used the wrong sign here. So declare and initialize. But we actually have to search inside the slice. So for every element that we expect, we have to search the slice elements and check if we can find it. So we assume that it has not been found yet. And then we say, let's name this expected and this one element. So if expected equals element, then we found it, and we can say found assign true, and we can break the inner loop, leave it, and don't have to continue searching. Then, of course, we need to verify if we found it. If we didn't, we want to fail the test because there's at least one element that is not contained in the slice. So I'm going to call fatal F, expected to find this, but slice is that. Okay, so pretty simple, right? Our first loop is responsible for iterating all the elements that we expect. And the second loop for each expected element actually runs through the slice. So you may know that this is not very efficient if you got very large slices. Like if this is a very large slice with millions of entries and this too. But for our testing purposes, we know that this is not the case. So we're going to add a comment here, which is a good practice. Since our use case covers rather small element counts, searching with a nested loop is fast enough. You won't really notice a difference here unless you go really crazy with the slice sizes. Okay, let's see what the test says. And it says expected to find red, but slice is empty, right? Because we didn't implement the slice method yet. And what we need to do is we need to copy all key values from the internal map into a new slice. So very straightforward. This time, just as a quick refresher, let's use the make built-in, where you can pass certain types and the size. So I'm going to create a new slice. And size needs to be the size of the map because we got as many elements in there as in the map. Now I'm going to iterate with a classic index loop. So using an integer that we increment after each iteration. And I'm doing that for the whole slice. But actually, wait a minute, we can't just iterate the slice. We need to iterate the map in order to get every value. So instead, we basically have to do it like this. We want to say get the key, which is our element, in range s.internal map. And then we say that slice element at index is assigned the element, and we must not forget to increment the index. And of course, at the end, we return this new slice and not an empty slice. So let's see if this works. And yes, it does. It passes. Another way to write this, probably a bit more simple, is to just use append. But then we must not specify the length here, I believe. So let's test this. Or let's say we want to omit the index and just use append, then slice will become append slice element. Let's see what happens. It passes, so this is still fine. Let's actually print the slice here, just as a quick visualization. And as you can see, by appending, we are actually not using the element space that has already been created, but instead we are adding new elements that append allocates for us. So that was different when we used the index accessing. There we used the elements that have already been allocated by make. So if we want to use append anyway, we can specify the length to be 0. Then append will start with the first element and it will look like this. You can even go further and you can provide the capacity. So we know the size needs to be the length of the map. So we can actually say prepare a capacity of 3 or 4 in these cases, but that just means that there's enough space under the hood for so many elements before we need to allocate more memory space. The length is 0 nonetheless. We also specified that here. So append starts with the first element. That was just a side note. So if you didn't quite understand the details, don't worry about it. Just remember that append adds new elements, and if you already have the space for the elements allocated, then you will probably want to use indexed access. So our test is happy, and that means there is not much left for us to do. I want to add one more method here. That is a string method. So if you've seen my video about methods and interfaces, you may know that there's a standard interface stringer that we can implement for printing string representations of types. For example, our set struct. It just needs a string method without any parameters and returns a string. And what we're going to do is we will build our string by just appending the content and making it a comma separated list. So we can basically say appended. So for each element, which is a key in internal map, we append the element. And if we already have some content in the string and it's not right at the start where it's empty, we add a comma and a space for readability. So you can do that by checking the length. So if length of string is bigger than 0, then it means it's no longer empty and we should add this separator. And remember, this is a shorthand basically for writing string plus element. So it adds to the existing. It also works for integers. And we can shorten that a bit by writing it like this. And then we need to return the string. Now there's one aspect about that we already talked about it briefly in the slice method. The order of the elements is not static. So maps by itself, they are built for fast lookups, and you can't rely on any ordering. If you need ordering, you should use slices or other data structures that are built for that. So even though we create a slice here, the source is the map and it doesn't have a well-defined order. In this case, it's fine. We accept that. In the case of the string, we want to make sure that we return elements in alphabetic order. So return elements ordered ascending. And that is pretty simple to do. There is a sort package in Go I already touched on it in an earlier tutorial. And we can use sort slice, I believe. Was it string? String slice, right, from sort. But it expects a slice of strings. So we can actually simplify this even further and use our slice method. So we can reuse this code to create a slice of strings. And then we can sort it with this built-in functionality. And then we have to make a string out of it. So let's see, what does the documentation say? Value of type sort string slice is not used. All right. That is because we don't yet do anything with it. So since this is a slice and we want to return a string, we have to make sure that the slice is converted to a string. And of course, there's also a handy function for that. In the strings package, we can say join. And as you can see here, you can pass it in a slice of strings and a separator, and you get then a ready built string. So when we say slice and use comma space as separators, then it joins all the parts together using this separator. So we don't even have to write a loop and the distinction. If we need the separator ourselves, we can just use this library function and reuse our slice method. Pretty cool, isn't it? So we didn't yet write a test for it. Let's make sure that we got one in place. And as you probably already saw, we need a check function for strings. So pretty much a lot of code repetition here that we can improve upon later. So when I call set.string, I expect to see it in alphabetic order. So green first, comma separated, followed by red and yellow. Blue is not in there yet. Then here it should be blue at the beginning. Blue, green, red, yellow. And when red gets removed, blue, green, yellow. So that is it. And let's see if that works. So it fails in line 13. And that is probably because we missed something. Okay, so it's not sorted yet. Got red, green, yellow. So G comes before R. So something is wrong about our sorting. Let's actually write a little debug print here. Okay, and as you can see, it is not sorted. So why is that? We're actually calling string slice. Is this the... we just used the wrong... something wrong. So we just referenced the type, which is a string slice, and that is why it actually compiles. So this is just a type definition here, but it doesn't really do what we want it to do. Instead, we want to sort for strings. And the function is actually called strings. You can see it here that this is a method and this is a type. So interestingly enough, we just called the wrong place. And actually it doesn't require us to assign any parameters because it has no return value. So just call it like this. So good that we had a test for that. And now it works as expected. And that's about it. That's our very simple but functioning set implementation. We saw that sets contain unique elements. If you add elements with the same value multiple times, there's only one of them inside. The lookup is as fast as for a map, and you have seen under the hood we're using a map, but we're not really interested in the value. We implemented a new function which is useful to create new instances of types, and we implemented several methods that are helpful for us so that this is actually useful for some use cases. Now you may already have seen that while this code can be reused for string elements, it is not flexible enough to be used with other types. So let's say I want to add integers. So something like this. 1, 2, 3, 1. Then I can't do that. It says cannot use one untyped int constant as string value. And usually that's a good thing that the compiler checks for type errors. It can prevent a lot of subtle bugs. But we actually want a data structure that is generic enough to have this characteristic, store unique elements, fast lookup for different types. And that is where we are going to continue in the next video, where we will see how to make this work without having to copy paste everything for the new type. So naively we could say, okay, then let's switch to int, but then I can't use string anymore. Now I could call this set string and create a copy for the type and all methods for the int type. Sure, we can do that, but that is a maintenance hell. So in the long term, you have a very difficult time to maintain that for every type that you want to use the set with. Moreover, it's a bad practice and it is really error prone. So sooner or later you will introduce errors because you can't keep every implementation in sync. Let's say you add a new method and you need to remember to add it for every set element type. Fortunately, in basically all programming languages, there are ways to fix that. The next video will look at the first approach that doesn't quite need the new feature of generics, which is the empty interface. And it is basically an alternative of writing this in a very flexible way, so you can reuse the code for different element types. But for this video, that is it. I hope you had fun watching it, and as always, I encourage you to try it out, get your hands into practice, and leave a comment. If you liked my content, feel free to like it. Tell me what you want me to talk more about in the future, and see you next time.